machine learning are on forecasting stock prices, and with good reason. If you can actually do that, you can make a ton of money. But there has been less research, comparatively speaking, on the corporate finance side. So here we're trying to look at a corporate finance application that is also related to valuation, but again, more on the corp finance side.
Pointed to the machine, so.
Did you break it wrong?
It was working with red, so.
Yeah.
I also needed for the right angle.
Well,
I click it and we'll.
I think I'm there. Yeah. Okay. Perfect. So now it goes. So again, the goal of this paper is to try to predict systematic risk for private companies. Companies where it's kind of hard to figure out the amount of systematic risk that they have. If this was publicly traded companies, figuring out the systematic risk is not so hard, but figuring out the amount of systematic risk in a non-traded asset is a little bit more complicated. So why is this relevant? Systematic risk is a crucial input for discount rates, which themselves are a crucial input for valuation. So why would we want to value a non-traded asset? It happens all the time, mergers and acquisitions. A publicly traded company is buying a private company. They decided to pay X amount of money for it. Why did they decide to pay X? Well, we hope that they did a valuation exercise one way or another. The classic way that we teach our undergraduates to do valuation, discounted cash flows. This means think about the cash flows in the future, bring them to present value using a discount rate. But figuring out the discount rate in private companies is kind of hard in non-traded assets. So this is where we believe that we can add some value. Why is machine learning helpful here? So there are already methods that cannot deal with this. Why do we expect that using machine learning would be better? Well, first of all, this is kind of like a prediction problem based on an observable profile of a firm. Try to figure out what is the systematic risk in that firm. So machine learning is pretty good for prediction. So we feel like there may be a chance here that it can help us. Also, machine learning is pretty good at handling many predictors, where some of them or many of them could potentially suffer from collinearity. And because we can have a profile that is very extensive for a firm, this means many variables, many firm characteristics. ML methods can help us to select the better ones. And last but not least, ML is also great at uncovering nonlinear effects. So how firm characteristics translate into systematic risk in an asset. It might not be just a linear function, it may be nonlinear. So again, ML might be good here. So some background. First of all, systematic risk, we're gonna use that interchangeably with a firm's beta. Think of it, the cap and beta. It may be or may not be the case that beta captures all of systematic risk. Most likely it doesn't, but trying to keep it simple. We're just going to look at a firm's beta, and that's going to be kind of like our measure of systematic risk. And the idea is, can we figure out kind of like a way to estimate this beta? Again, if we're talking about a publicly traded firm, this is very straightforward. I'm pretty sure we've all run regressions, CAPM regressions, where you get the beta. If you can observe market prices, you can get the returns, and then you can get the index returns, and then you can run your estimation, and you get the beta. Again, for non-traded firms, it's a little bit more difficult because there are no observable prices. So there have been two alternatives proposed in the literature. One comes from the finance literature, another one comes more from the accounting literature. So from the finance literature, this comparable company analysis, sometimes also referred as a pure play method, which builds on all theoretical work from Hamada all the way back to 1972. In the accounting literature, there is this concept of accounting betas, again pioneered by an older paper from 1970 by Bieber, Kettler, and Schultz. It doesn't get a lot of play on the finance side, and I'll talk briefly about why that's the case, but this has been kind of like the two alternatives in the literature, and we want to see if we can improve on them. So just some background first on this comparable company analysis, which is kind of like the method that has been proposed on the finance side. for figuring out the beta of a non-traded asset. So this paper by Hamada, 1972, had the insight that a firm's beta or systematic risk is a combination of two things, what he calls asset risk, and then the capital structure of the firm. So the business line of a company generates some risk, just kind of like using your assets to generate cash flows. That generates some risk. But then how you fund those assets, the amount of leverage that you have, how much debt you have, then all of that gets reflected in the equity risk of that firm. So this is kind of like if you ever done these valuation exercises in some advanced undergrad or maybe in a grad class, sometimes you talk about an asset beta. And that's kind of like the insight that Hamada has. That equity beta, the overall capital beta, is a combination of two things, asset risk and capital structure. So this method, the CCA method, the basic idea, and it's pretty simple, I think, pretty straightforward. Of course, it relies on some sleights of hand. Find a publicly traded firm or firms, find a group of publicly traded firms that you can observe that are in the same business line or in very similar business line with similar assets to this private firm or this non-traded firm. Because these two firms are in similar, or this group of firms are in similar businesses and they have similar assets, they should have similar asset risk. So you can use that as a proxy for the asset risk in your private firm or in your non-traded asset. Then you just adjust for differences in the capital structure. And then this is how you recover or you get an estimate of the systematic risk in the non-traded asset. Pretty much you use a stand-in for the asset risk that you can observe in a different company. Bauman and Bush, they claim that this method is the standard tool in the finance industry to measure beta or systematic risk for non-traded assets. In our paper, we also have a little bit more evidence where the CFA Institute seems to suggest the same. So this method seems to be kind of like the standard. And probably for some of you, again, if you've taken a evaluation undergrad class, you've probably done something like this. We don't really have to go into the math here, into the equations, and they're not that hard. But the basic idea is, and this is coming again from Hamada 1972, this V subscript U, this represents the asset beta. In most textbooks, we use the U because it's also referred to as the unlevered beta. So I'm pretty sure you all know that in finance, we tend to call the same thing by different names. So this is one of those cases. Asset beta, we also call it unlevered beta. That would be what is the asset risk on this side. This is the regular CAPM equity beta. And then this is an adjustment for the capital structure of the firm, where this represents debt, this represents equity. Just to get to this equation here, you have to actually do some assumptions, which is what Hamada does. He proved that under some conditions, you can have this relationship between the asset risk in a firm and the risk in its equity, or the systematic risk in its equity. The basic idea is, well, this asset risk, I cannot observe it for the non-traded asset, but maybe I can get it for the publicly traded firms. I can get the beta for those firms. I know what the debt and what their equity is. So I can actually back out that asset beta, asset risk, unlevered beta, all these are the same terms, for a group of firms. And then I use that and I plug it back in using now characteristics of the non-traded firm or the private firm. And then I get an estimate for its systematic risk. The other method, again, coming from the accounting literature where they look at accounting betas, it's very similar in spirit to what the CAPM would be, except that instead of using market returns, you use an accounting measure of earnings. So this is, again, probably why it hasn't been used in finance, I think. So in finance, at least finance professors, we like to argue that the market is looking forward into things that have not happened yet. Accounting things are looking into the past, into things that have happened and that are not really that important for the future, perhaps. But anyways, in the accounting literature, the basic idea is, all right, if you cannot see the market prices for the asset, at least hopefully you can observe the accounting earnings for the asset, and then just find the co-movement between those accounting earnings in your private company and the aggregate market earnings. And then that co-movement is like your systematic risk, just like the cap and beta is the co-movement between the return in the company and the return in the aggregate market. And again, in the accounting literature, this has gotten some play. This paper here from Elaki in 2021, they kind of show how to compute these accounting betas, and they actually show that they do seem to capture systematic risk, and they seem to be priced in the cross-section of traded firms. So where is our contribution? Well, if we're going to make a contribution, we have to say that, well, there is something where these methods here are not working so great and they could be improved on. So in a seminal paper in the literature, Leslie and Payne, they show that these betas coming from the comparable company analysis, they give you a pretty good idea of the systematic risk if you are trying to value a portfolio of many companies. Say you have 100, 200 private companies, and then you get what is the average error in that systematic risk estimate, and the average error is actually quite small. The problem lies in that if you're not trying to value kind of like a lot of companies at the same time, so if it's not a portfolio of 200 companies, what if it's only 1, 2, 3, 4, like a handful? In that case, this method is awful, and it's actually pretty hard to get traction here. The mean absolute error is quite large. So the way to think about this is that this method produces errors that have a very, very large variance. So if you are, say, an equity analyst, and you are advising on a merger and acquisition, and you're trying to use this method to value a private company, it's only one company, chances are that this method is going to give you an awful result. It's not really going to be good. Now, if you were trying to value, again, a portfolio of 200 private companies, the portfolio, in the end, might actually not be too bad in the valuation aspect. But if it's, again, only a handful of companies, because of the large variance in the errors, it's going to be pretty bad. The accounting betas option really has not been tested in the literature. Again, this is coming from accounting. It's mostly used in accounting settings, not so much in finance settings. So it's an open question how this one really behaves. And we are testing if machine learning can improve on this. And in particular, kind of like in the setting where, say, you are only looking at one company or a handful of companies, right? Which we think is the more relevant setting in practice. So we are trying to look not at the average error, but at the average absolute error. I'll talk a little bit more about the methodology that we follow, but it's very similar in spirit to these models, where we're actually going to use predictors that are coming from a peer group of firms, capital structure variables, and just financial accounting variables. So we're taking kind of like the same idea that these other two methods that are out there are using. We are just repackaging them in an ML framework and see if it works better. One huge caveat that we have to make in all of these papers, even the ones that have proved the comparable company analysis before, we are trying to forecast the systematic risk in non-traded companies or in private companies. But due to data availability, it's actually pretty hard to do because, I mean, we don't really have data on private companies, so the data is pretty sparse. So what we do in these cases is that we take the publicly traded companies and then kind of like treat each one as if it was private. And then kind of like say, all right, suppose that this company is private and I need to forecast the systematic risk of this company. And then you move on to the next one and to the next one and to the next one. So kind of like we're trying to figure out whether this is a good or a bad method. But actually using publicly traded companies, make believing that they are private, which is not exactly true. And that also brings its own issues because publicly traded companies are not exactly the same as private companies. We'll deal with that in a little bit later. So the main takeaway, in case I run out of time here, the machine learning algorithms perform much better. They lower these mean absolute errors by over 40% relative to the comparable company analysis. Even models that are much more parsimonious, where we're not really using a lot of variables or anything like that, a lot of predictors, they still have massive improvements over the comparable company analysis. The overperformance seems to be at all points in time, at least in our sample, and for really all groups of firms. So even doesn't matter how we segment the sample, ML methods seem to just be better. And it's always hard, or it's always a sketch to try to guess why ML methods are better. They are a black box in the end, but we believe that they look better. Not really because they're using a lot of variables and kind of like figuring out this multicollinearity problem correctly, that they're selecting the right predictors, but rather because they are finding kind of like nonlinear relations. And I'll talk about that in just towards the end of the presentation. Hopefully I have the time. All right, now, the empirical methodology. So we're using the CRISP and CompuStat data set, the intersection from 1980 to 2021. But the first 10 years, we're just going to use them for pure training. So the actual forecasts are going to be done 1 year ahead forecast. From 1990 to 2021, we keep only trying with December 31st fiscal year end. This is because there is just we're going to keep match between market data and accounting data. So we kind of have to do this. It's also something that I think has been done in the literature, at least in this subject before. We get rid of financial utilities, companies that are not really that large. Our final sample consists of close to 65,000 third-year observations with over 6,000 unique firms. And we're going to define industry, which is how we're going to define the peer group of a company. Do they belong to the same industry or not? At the 2-digit FIC code. But here we should say that it really doesn't make a difference if we bring other definitions of peer groups and industry. Whether we use different industry classifications or not is not really affecting our results. How do we estimate the systematic risk in companies? So everybody that has run a regression knows that when you get a regression, you get a point estimate, but that point estimate is not the ground truth, right? A point estimate is just that, a point estimate, and then you have uncertainty around it. You have standard errors, you can construct confidence intervals, et cetera, et cetera. So even if we have a publicly traded company and we can observe its returns, how can we be sure about its systematic risk? So we follow this realized beta concept from Anderson et al., where they pretty much do just a covariance. I mean, that's like a regression coefficient, covariance divided by variance. And under weak regularity conditions, they find that this is a consistent measure of the underlying beta. It's pretty much like running a regression, I guess, like running a kappa regression. We use a few algorithms here. We use 3 types of decision trees: random forest, XGBoost, like GBM, and we use 2 flavors of feed-forward neural networks. This is always a double-edged sword, I think, using multiple models, which is always recommended in machine learning, right? But I mean, I could have used 20 models here, 20 algorithms to forecast. Even if they were all junk, just by random chance, 1 or 2 of them would have done better than the other methods. Just because I'm using so many algorithms, I'm just gonna get lucky, right? And it's just random chance. So this is always one of the dangers of using a lot of models, right? One of them is gonna be better, but it could just be random chance because you're using a lot. On the flip side, what ends up happening here, actually all of them are better. So that actually gives you some comfort that this is not random chance because all the algorithms are actually doing better. I should also say here for the neural networks, we are not really tuning them. So the architecture, for anybody that has worked with deep learning, the architecture has infinite possibilities. We are just setting 2 architectures and that's it. One has 5 layers, the other one has 9 layers, but here you can really go crazy with the architecture. That was not really our intention here, to spend a lot of time on just figuring out which is the best. But let's just go with it. These are the predictors that we use. We use 58 predictors. We can group them pretty much in just these broad groups. We are getting information from peer firms. So any company, when they belong to an industry, you have the other companies that belong to the same industry. And we're grabbing kind of like the peer firm data. Then we're also getting financial statement data from the company itself. So measures of size, measure of capital structure, and then other measures coming from the balance sheet and from the income statement. And finally, we're getting macro variables and industry variables as well. So this is a very robust group of predictors. And later on, we're gonna do some robustness tests just to see what happens if we actually don't have access to so many predictors, which probably is what happens in real life. But before we just get to show the results, because we're talking machine learning, we have to do some hyperparameter tuning here. So the way that we do it, and it's much easier just to see here, although the colors here are not coming as I thought. When I was looking at it on my screen, it looks much better. But because we have a time series here, we cannot really do cross-validation or anything like that. We actually have to do the walk-forward validation. So when we're trying to forecast for year t, we are going to use these years t minus 10 to t minus 3 to just test a bunch of different hyperparameters. We're going to validate them in these 2 years, figure out which one is the best, and then forecast for year t, and then move everything 1 year, and then we just do it again for year t plus 1. And we kind of go like that in this moving window validation. These are our main results here. So we have a bunch of models here. The CCA is this comparable company method that I showed you. The AV represents the accounting betas. And depending on which flavor of accounting earnings you want to use, you can get different versions of that accounting beta. These are the ones that have, as far as we could tell, have been the more popular ones in the literature. So whether you can use return on equity, this is a measure of fundamental return, which is just going a little bit higher on the income statement using EBIT instead of earnings, or if it's the actual change in earnings. And then here we have all of the machine learning methods. And really the column that matters, I think, is this one. This represents the reduction in percentage terms in the mean absolute error with respect to the CCA method. And again, we're getting reductions of around 40%. The best method, which is the boosted trees of light BBM, which is a good thing because it's also the fastest method to run, gives us a reduction of 42% in the mean absolute error relative to the CCA. I should also say here, just because we're in this slide, all these accounting betas are horrible. They do pretty bad here. And that may explain why they really have not been used in finance before. Again, in the accounting literature, they're used for different stuff, not so much for valuation. But at least when we plug them in here, it's just awful. Kind of like they have lots of errors. They look to be pretty biased. And again, the mean absolute error is just humongous. But all of these machine learning methods seem to do better. And again, this is the point where we are fortunate that we did several models or several algorithms and not just one. The fact that all of them do much better kind of gives us some reassurance that actually we are getting a result that is true, we hope. Then to figure out which variables seem to matter here, we do the permutation importance. Ren already talked about that, so I'm just gonna go straight with the graph. It's kind of hard to see, it has a lot of variables and whatnot. I just love doing heat maps, so I love showing this, but the darker that it is, the darker the red, the more important that it is for that particular model. The lighter the color, the less relevant that it is. So, of course, every different algorithm has different places, different values on these variables. But it seems like the most agreement is coming actually from the variables that Hamada said that should matter. It's coming from industry peers, and it's coming from some measure of capital structure. So at least this also kind of gives us some reassurance that, all right, all of these models, they are black boxes and whatnot, and you can throw them in there. But at least the variables that seem to be powering up the predictions actually seem to make sense with the theory, at least. Then we do some robustness here. We have to be careful here because we're using publicly traded firms and then make believing that they are private, which is definitely not true. And we're using 58 predictors. Really easy to get when you have access to CompuStat and CRISP, and you can just program everything and then just get it. But if you really want to use this method in practice and you're looking at private firms, it might actually be kind of hard to actually get these variables, these audited financial statements and all that. So our results here, are they being better just because you could never replicate this in practice? And also, because we're looking at these publicly traded firms, I mean, we know that private firms are different than publicly traded. They're usually smaller, they're usually younger. So, some robustness study here. We do again our ML methods, but we use a much more parsimonious set of predictors that we argue would not be that hard to actually get for even private companies. We use all the variables that are coming from peer firms. That makes sense. These are publicly traded, should be accessible. Then we just use a measure of size, which is just book assets. And then we just use a standard deviation of return on equity and return on assets just to kind of get a measure of the riskiness in the cash flows. Even for private companies, we argue that these variables shouldn't be that difficult to get. And to figure out what is the impact again on these smaller and younger firms that are private, we actually break our sample by quintiles based on size and based on age. And the results that we get are very reassuring. So our best performing algorithm in the previous exercise still does really well. It still reduces the error close to 40% relative to the CCA. The performance is not so great. It has reduced. It used to be close to 43%. It has gone down now to 39%, but still way, way better. And then when we split our sample by size and age, the first quintile is the one that we really want to look at because this is the one that will be more similar to private companies. These are the public companies that are smaller and that are younger. And we find that even here, we have like very good overperformance coming from the ML model relative to the CCA. And again, this gives us some reassurance that actually this method will be good in practice. We do some additional analysis here. I'm gonna skip it because I think I'm running out of time. I'm just gonna show one last thing here. This is a partial dependence plot. It kind of tries to show how the prediction changes with changes in two predictors. Here we look at two predictors that seem to be important. This is kind of like the asset beta of the peer firms. And then on the y-axis, we have leverage. And the pattern here that we find that seems interesting to us and that maybe tells us a little bit of why these models, the ML models, do better than the previous literature, is that for very extreme values, in particularly of the asset beta, so think of it like the extremes here, the prediction tends to go toward the middle. So the prediction is not extreme. So you can get very extreme values in one of the inputs, but some way, somehow, the algorithms recognize that, hey, this is too extreme. If I'm gonna make a prediction, let's not use this. And then it makes like an unconditional prediction. And the prediction kind of goes towards the middle and just kind of like disregards it. So we think that this may be part of the reason of why these ML models are better than this CCA. In the comparable company analysis, it's very straightforward. If you get a very extreme value in the inputs, you get a very extreme value in the outputs. But in some way, again, the algorithms here are kind of figuring out that if I have a very extreme value in the inputs, let me disregard it and then just give like an unconditional predictor. So that seems to be kind of like a safeguard against just doing dumb stuff. And that's it for me. Thank you. Questions? Did you answer all the questions?
Yeah.
We'd like to regular classes.
Yeah.
I think yes, no.
So maybe one of the potential robustness test you can possibly do. Maybe I'm off the topic, but so there's an industry average you put in the predictors. I was going to say that maybe after the fact that you calculate the new data, you can compare to industry average, but one of them is already predictor, so you cannot do that. But the other thing is that maybe you don't have the data, but suppose that there's some set of a firm, either LBO, then they used to be a public company, but later they changed to the private company. Then perhaps the only things that you have changed is probably capital structure is way over leverage because they did the LBO. So perhaps you can take that sample and calculate the new beta using Hamada, and then maybe compare that to your machine learning predictor beta as a checking measure. I guess that's the one thing, and the other thing I was thinking, perhaps maybe this is another paper, I don't know, but
Okay.
That sounds good.
so instead of doing supervisor, you have all the predictor, especially those top ones that you saw the last slide. If that has a really predictive power, that using those predictive variable, you can do the clustering. Then you identify some clustering firm and just check the median value and average value as a new data. Maybe that, I don't know, that might be.
So about the first point, yes, we're thinking about that, and that's one of the things that we have thought about how we can actually use this in private transactions. And we're still thinking how we find the data and all of that. But yeah, that would be a really good use case for this, and hopefully a different paper. On the second case of the clustering, unfortunately, that has been done.
Oh, okay.
I mean, not necessarily with this method, but with some slightly easier method, the KNN, perhaps the random forest. I mean, it's just like a higher dimensional version of the KNN. But yeah, it has been done.
Okay.
The question?
Yeah, I just wanted to ask, in terms of sort of market for corporate control and liquidity discount or premium in the private company sector, obviously there's no real market for corporate control, there's transparency. I mean, I read in various things that the private multiples for private companies are actually much higher than listed companies. In fact, and that's why that whole industry is potentially having some problems now. In your work, did you come across any salient trend in liquidity? I would have thought discounts for those, but actually they appear to be premiums. And are there any explanatory variables that drive people to pay up for those kinds of companies?
So when we look at liquidity, we look at aggregate public market liquidity and kind of like those type of variables. But I understand what you're saying. The way that it typically is done, at least in textbook cases, is you will get, say, the beta of the company, and then you adjust it for size, and then you adjust it for illiquidity and whatever other adjustment you want to do. And a lot of that is very rules of thumb. Like there is a 30% illiquidity premium, or I mean, you just give it kind of like a number, right? And you can, you can pretty much make it any number that you like that then justifies the value that you're paying for it, of course.
Calibration.
Yes, yes, I don't want to say that. Our method here would be for finding kind of like the first estimate of the beta, and then you could adjust it if you want to place additional value and control. You could adjust it based on that. But yeah, it is a very interesting question because I think these adjustments that you do after you get an estimate for your beta and then you adjust it for the other things just gives you so many degrees of freedom to play around with. It's a very interesting question how you can actually corral kind of like the degrees of freedom that analysts get in those cases so that you cannot simply just justify whatever number you begin the process with. Yeah. Okay. Thank you.